All right, let's quiet down now. Grand. Now, are you all ready for some electric circuits? Yes. Good. What I'm going to teach you today is how to write down the equations that describe the flow of charges in electric circuits, even electric circuit networks. It's a very easy task. There are very straightforward rules, and you will learn now how to analyze also the behavior of these circuits. Let me remind you what we spoke about at the end of last day. We talked about where one finds charges in the atmosphere. We talked about plasmas, such as, for instance, the solar wind, or what you see in the atmosphere near the north and south poles, where the charges come in along the Earth's magnetic field and then collide with the air and cause lots of interesting behaviors. We talked about electrolytes, but mostly now we're going to be talking about currents flowing in wires, conducting materials, conducting wires like copper wires that make up the circuits. Now you can have the picture of a circuit in mind, but in fact, a lot of the ideas go over to transistor electronics and all the sort of modern circuit boards and circuit systems that are very much miniaturized. But in a sense, we can think about them in the way we will draw them up this morning. What flows? Charges flow. Sometimes the charges are positive, ions. Sometimes they're negative, like electrons. In copper wires, it'll be mostly electrons that do the flowing. So charges flow. How do you measure the rate at which charges move along a wire? Well, we measure the current. It's the rate of change of the charge with respect to time. And you need also, because of resistance, you need to actually push current through, or push the charges through the electric wire, just in the same way that you need a pressure head to push water through the plumbing system. Because you have friction, natural friction in the plumbing system, the water adheres to the walls, so it needs an extra pressure, more pressure here than here, in order to push the fluid through the pipe. It's similar with electric current. Now, the first thing we're going to learn about here is, what are the circuit elements? Basically, there are four that we will deal with. The first one is the resistance. The resistance. The resistance, we usually draw it as this jagged line here in the circuit. Come on, chaps, you're late. In you get. Sit down. This is the resistance. Now, if I have a voltage A, VA here, and a voltage VB here, then there is a very simple rule relating the current, the resistance, and that voltage difference, like the pressure difference in the water pipe. This voltage difference is proportional to the current that flows, and the constant of proportionality, R, is called the resistance. It is measured in units called ohms. 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 Now, you might ask, you might say, well, is that a law of nature that the voltage difference is proportional to the current? Or is that just an approximation? The answer is it's just a good approximation. If for fairly low values of the current and the voltage difference, the law relating the two is linear. We will always treat just linear cases in this course. Okay? We will treat just the cases where there's this linear relation. And sometimes then what it's called is linear circuits. Linear circuits because of these linear relationships between the voltage difference and the current. The current, the letter we use for current is I. It'll also turn out to be the letter I will use to describe the square root of -1 when we get to that next week. But we will stick with the I for current. Then we have a capacitor. The capacitor kind of is like a battery. It stores charge. Maybe plus charges on one side, negative charges on the other plate. The voltage drop across a capacitor is proportional to the charge on the capacitor times a constant. That constant is called 1 over C. It's called the capacitance. The capacitance is measured in farads. Third, henries, inductance. This is to do with sort of magnetic effects. You have this, we represent it as this coil in the circuit, in the wire in the circuit, and the voltage difference across it, it's not proportional to the charge or the current, but rather how the current changes in time. So in a situation where the current is changing in time, like maybe sinusoidally, then the voltage difference changes sinusoidally in time as well. Finally, we have the source. The source, what drives the current in the circuit, is the EMF, electromotive force. You could think of that as the battery that you're going to apply to the whole system, or some source. And we represent that with this circle with a squiggle in the middle. And usually the voltage across that will be some given function of time. For instance, a little later on today, I'll be deriving for you the equation for an LRC circuit, okay, in which the voltage given is in fact the signal that you get from, say, some radio station on the aerial, which is going to drive this circuit, which is eventually going to make music on your radio. So, these are the four elements we will deal with. They're the ones in which you meet always first. Now, there are other elements. There's things called diodes. Does anybody know what a diode does? Well, it's a kind... Yes? Were you going to say?
It's the direction of the...
Very good. It's a directional resistance. It's something with the property that it's very easy for the current to flow one direction and very hard for it to flow the other. So we're not going to have diodes in our circuits. We will study in the third part of the course a thing called the van der Pol oscillator, in which the current is related not only to the voltage drop, but to the voltage drop plus a little bit of the voltage, the cube of the voltage drop. And that's a nonlinear relation, but we will actually have the capacity to handle that with the material we'll get in the third part of the course. It's has very interesting behavior, this van der Pol oscillator, but for now we have these simple ingredients. So now the next thing I have to tell you is, what are the rules? The rules. So circuit rules. And they're due to a fellow called Kirchhoff. And they're very simple and very natural. Rule number 1, K1, Kirchhoff 1, says that if you have a wire running along and it splits into two wires, or one bit goes this way, one bit goes this way, then the current flowing, the net current flowing into the junction is zero, or another way of putting it is the current that flows in is equal to the sum of the currents that flow out. So I equals I1 plus I2. This simply reflects the fact that you can't destroy charges. If you got stuff coming in and stuff going out, there's no way of destroying stuff at the junction, then the total stuff in has to be the sum of the total stuffs out. And the stuff in this case is the charges. And that's represented by the current. The flow of charges into a junction is equal to the sum of the flow of charges out. I equals I1 plus I2. Very simple. The second law is as follows. Around any closed circuit, so I'm going to draw a circuit here. This is a switch. Maybe I have a source of EMF here. I have a resistance. I have maybe a capacitance. So like that. And actually I may have another bit of the circuit, so the we could have a network like this. A, B, D, F, G, H. I will just designate the corners by that. The rule says around any closed circuit, the sum of the voltage drops is zero. So, I'll give you an example. For instance, take the circuit ABGH. VA minus VB plus VB minus VG plus VG minus VH plus VH minus VA has to be zero. It's very natural, because what it says, another way of looking at it is, the voltage drop from here to here is the same as the sum of the voltage drops around those three legs. Right? It's very simple. It says that the voltage drop, say, from here to here, the sum of the voltage drops from here to here, here to here, and here to here is the same as the voltage drop from here to here. So the sum of the voltage drops going round like that is VA minus VB, VB minus VG, Vg minus Vh, and that's equal to Va minus Vh. Only in this case, I brought it to the left-hand side, and instead of expressing it that the sum of the voltage drops around any two loops, one going this way, one going this way, is the same, I'll just say the total voltage drop if I go around a closed circuit is 0. And that's it. Armed with this and with this, you are ready to write down the equations that describe how current flows in any circuit or any network of circuits. Let's take our first example. Right. What we're going to do is charge up a capacitor. So example 1. Charging a capacitor. Here's the situation. I have some external source here that I'm going to use to provide the charge. I have a resistance here, and I have a capacitance here. So this is A, B, D, F. I don't use C in lettering the corners because we use C for capacitance, and we also sometimes use C for the coulombs in the charge. We have here a resistance, and we have a current flowing, I. And we have charges sitting on the capacitor here. And they may change with time. The charges, the amount of charges at the beginning, we may have no charges. No plus and minus charges, but we want to build them up here. So the Q of t, the charge is going to increase. We'll have, say, the pluses on this side and the minuses on this side. At the beginning, there's no pluses and no minuses. But we want to kind of put a charge here on this capacitor. This is like a battery that we're going to use later on. We want to pump it up. This is a switch. This is the sign I use for a switch. And it's when the switch closes, then current will begin to flow in the circuit. I'm going to give you, given that VA minus VF, that's this jump here, when you close the circuit, is some V0, constant. Okay? So, when we close the switch, this voltage drop here, given by what's the power source here, will be V0. All right. If the charge changes with time, the current will be related to the charge by dq by dt. Right. Now, we're going to use our simple laws, the rules. Kirchhoff 1 doesn't really apply because the current just flows all the way around the circuit. There's no splitting of the current. We just have one loop. Kirchhoff 2 says the following. Kirchhoff 2 says that VA minus VB plus VB minus VD plus VD minus VF plus VF minus VA is 0. So now, what is VA minus VB? We look at the circuit's elements. In other words, what is in here? In this loop, we have a resistance. So the current is I. The resistance is R. So what's VA minus VB? Ri. VB minus VD. The voltage drop across the capacitor is what? Q over C. The voltage drop across here, there are no elements in here. Zero. This is a kind of cartoon. Of course there's a little resistance in the wire, okay? There's a little resistance in the wire, but we're thinking in this circuit that most of the resistance is kind of holed up here in this particular large resistance R. So plus 0. And what's VF minus VA? Negative V naught equals 0. So, how many unknowns do we have? How many unknowns? What don't we know? No, we know the resistance. I give you the resistance and the capacitance, and I've given you the V0, but we don't know what the current is as a function of time. So we don't know that, and we don't know this. So I have one equation, but I have two unknowns. How are Q and I related? Right. We know I is dq dt. So this is the equation R times dq by dt plus 1 over C times Q equals V0. Wow. A first order, constant coefficient, ordinary differential equation describes how we charge up this capacitor. Let's take the initial condition here. That Q of 0 is 0. In other words, originally it was dead. The capacitor had no charges built up on it. Right, so now let's see if we can analyze this situation. Before I do, are there any questions? It's very simple, isn't it? I mean, the sum of the voltage drops around any closed circuit is 0. And if you have a network where the current is going to split at a junction, then the current in is equal to the sum of the currents out. Okay, that and the circuit elements and how the circuit elements relate current and charge to voltage difference across that circuit element. That's all you need. Now we come to differential equations. We shall solve this. This is a first order linear equation. With V naught constant, actually, we could actually also use the separable method. But we will treat it as a linear equation. So, to solve, I'm going to divide across by the R. So I have dq by dt plus 1 over RC times Q equals V naught over R. Integrating factor. What is the integrating factor? It's e to the integral of 1 over RC dt That's just e to the t over rc, because r and c are constants. So I multiply across by the integrating factor. So I e to the t over rc times dq by dt plus 1 over rc times e to the t over rc times q equals v naught over r e to the t over rc. I've just multiplied across the whole equation by the integrating factor, which is e to the t over rc. Why did I do that? What if I look at this guy, he is a perfect derivative. He is the derivative of the product of q with the integrating factor. That's what those two terms are. This is the d by dt of a product, uv. So it's du by dt v plus u dv by dt. So if I take the d of the first times the second, I get that term. If I take the d of this times this, the d of this is 1 over rc times e to the t over rc times q, I get that term. These terms combine to give me this, perfect derivative. And that's equal to v naught over r e to the t over rc. Integrate. I get what? I get q of t, e to the t over rc, equals, if I integrate e to the t over rc times v naught over r, what am I going to get? Right. You see, I'm going to pull out, it'll be rc times v naught over r e to the t over rc, which would be just cv0 e to the t over rc plus a constant. Now, what am I going to call the constant? We have so many letters here. We'll call it capital K. Good choice. Now, to determine which member of this family of curves, q versus t, in the qt plane, that I particularly want, well, I go to the initial condition. Q of 0 is 0. Q of 0 is 0. That implies at t equals 0, the left-hand side is 0. This is CV0 plus k is 0. So k is minus CV0. Therefore, Q of t is equal to CV0 1 minus e to the minus t over rc. I of t, what's the current equal to? Take a minute, compute the current. Anybody from Texas?
My dad's from Texas.
Your dad's from Texas. Good. Well, the chap beside you. What is the current? How is the current related to the charge? It's dq by dt. So if you know q, you find I by differentiating with respect to t. So differentiate this expression here with respect to t. That's right. I get nothing for the first term, that's a constant. So I've minus CV0 times e to the minus t over rc.
So negative CV0 over RC times that term.
Times the minus sign. So it'll be CV0 times 1 over rc. The c's cancel out, so it's just v naught over r e to the minus t over rc. Is that right? That's the current. Let's draw the graphs. Before I draw the graphs, was this clear? Solving the first order equation, yes.
So if you go to the line where you have the k and then go
Yeah.
up, go up one line,
Yeah.
you integrated both sides with respect to t, right?
Yes.
What happened to the right side?
The right-hand side, I integrated this with respect to t. The integral of e to the t over rc is equal to e to the t over rc divided by 1 over rc. Right? The integral of e to the at is e to the at over a. Right? So if I integrate this, I've got v naught over r times e to the t over rc over 1 over rc. The r's cancel, the c comes upstairs here. Okay. Right. So is this clear? Good, because I'm going to rub this out now, because I want to draw the graphs. I want to get some idea how I charge up this capacitor. Now, would you all draw this graph as a function of t? And also draw this one. There's Hunter here. Where's Izzy? Good. How do you draw that graph? Where does it start off? At t equals 0, what's q?
You'll have c times v sub 0 minus 1.
No, it's c times v0, 1 minus this. What's this going to be at t equals 0?
Oh, yeah.
So it's 1.
Times v sub 0, so it should be 0.
It'll be 0. So it starts off at 0. Okay, starts off here. As time gets very big,
Yeah.
what happens this guy?
Starts to decay.
It does. It starts to decay, and the current will end up at, the charge will end up at what?
C times v sub 0.
Exactly. C times V sub 0. So here's CV0. So the charge goes up like that. Okay. How about the current? What does the current start out at? The man in the green hat there. What's the current initially?
0.
Is what? No, here's the formula. I of t is v naught over r e to the minus t over rc. At t equals 0, what's this equal to?
V0 over R.
V0 over r. So, it starts off at V0 over r. Now, what does it do as t gets very large? I know it's difficult to see around that darn thing, but stand up, come up, take a look here.
Oh, I can see it.
You can. So what does this do as t gets large?
e to the negative t over RC will become very small.
Exactly. So it'll come down like this. It'll decay exponentially. So that's the current. Now, is that reasonable? Well, yes. I mean, you apply the V0, you bring on somebody else's battery, you hook yourself up, and the charge increases on the capacitor. You start loading pluses and minuses on the two plates. Okay, and the charge builds up to its final value of CV0. That's how much charge a capacitor of size C can hold. In other words, if you use a source of EMF with V0 volts, and you have a capacitor with capacitance C, you can hold CV0 watts. And what is the charge unit we use? Coulombs. So you build up to C times V0 coulombs. Now your battery is charged for a while. Right? So you've built up this charge, and as long as you don't allow leakage by making sure that you switch the switch off so that the circuit isn't connected, then the charge will stay up there. How long did it take to charge? Roughly, in terms of R and C. What is the time scale? I mean, the solution, this looks like CV0, 1 minus e to the minus t over RC. Now, so when I said before, take t small and then take t large, you told me when t was small, this was almost 1, because this is e to the 0. When t is large, this is 0, and so we move up here. But when I say small and large, I really have to say with respect to what? When I say t large, compared to RC, exactly. So for instance, if I ask, how long does it take for the capacitor to reach half CV0? In other words, to get to halfway. That gives me a typical idea of the time.
But it's 1/2 of RC?
Exactly, yes. No, half of CV0, half of its final charge. Okay? See, this would be the half CV. So I want to know, how long does it take, roughly, to get this far? Could you all calculate that? How long does it take to get, so what you want to find out is, we'll say how long, we'll call that t to the half seconds, because we're dealing in seconds. In a minute, I want to know when is qt to the half, I want to be half CV0. And that's equal to, of course, CV0 times 1 minus e to the minus t subscript a half over RC. See, this is how Q depends on t. I want to know the value of t, which I'm calling t subscript half, at which I get halfway. Your question and then yours.
I actually got the answer.
Yes, what's the answer?
The natural log of 2 RC.
Very good. Was that what you were going to say as well?
Yes.
Good man. But you'd have said it the other way around. You'd have said it RC times log 2.
Actually, yeah, I actually had that written down.
Now, does everybody see how to get that? Look, because the CV zeros cancel out. And so I have half equals 1 minus e to the minus t to the half over RC. So that means e to the minus t to the half over RC is equal to a half. Take the logs of both sides. I get minus t to the half over RC equals log a half, which is minus log 2. So t to the half would be RC log 2. So this would be t to the half would be RC log 2. So R times C, ohms times farads, has what units? Seconds, right. Ohms times farads is seconds. Now, Hunter.
When power is drained from the battery,
Yeah.
does it also happen, like, I guess?
We'll do that. We'll actually do a flash lamp in a minute. Okay? Yes, it does. You're right. It does. Decay exponentially.
So it drains faster at first and then very, very slow at the end.
Exactly. And what you want to get, usually in a flash lamp, you get it when it's in the beginning, and then you turn the whole thing off so that you don't waste your battery, but you've excited your little lamp. We'll get to that problem now. I want to do this quickly. Isn't it a good idea that I make R very small? Who thinks to be efficient I should make, if I make R very small, see I can't make C very small because the amount of charge I want to be on the battery is CV0, but I could make R very small, and then the time for all this stuff to happen would be very quick, right? T to the half would be small, and everything would happen very quickly. Now you're all practical guys. Is that a good idea? What do you think? Supposing I am hooking up this arrangement. I'm going to charge up this battery with this battery, this capacitor here with this battery, and I put in a tiny resistance. Not a good idea. Why?
I don't know. They just told us in E&M not to do that.
This young lady says it's not a good idea because they told us in E&M not to do that. Why?
I'm suspecting it might overheat.
Why would it overheat?
The charge be moving too fast.
Yes, and charges moving is current. Take a look at the current. What would the current be initially if you made R very small? Huge. You would burn, and most wires can carry a certain amount of current without heating up and disintegrating. That's why we have fuses, so that people like me, when we go to the lab, don't wreck everything. So the E&M, is this in physics? Yeah. Well, now do you see the reason now? Yeah. So you want to pick a happy middle. You know, you want to do the job fast, but you want to make sure, but you know, you can compute. The V0, you know what you're charging with. So you can pick your R so that the current that you generate, first of all, the largest current, because the current graph looks like this, the largest current is just when it starts up. You want to make sure that that isn't too big. Okay, and you know for most wires, you know, roughly what a network system will sustain before it goes psst. Right? Now, isn't that very easy? That's all this calculation, huh? We just know our elements, we know our rules, and voila. We have a complete description of the circuit and how it behaves. I expected you to burst into applause at this. Right. Now we're going to do another exercise. I'm going to have a network, a very simple network. And I want you all to help me write down what the equations are. And we'll come up with the final state, and we'll see if that makes sense. I'm going to do the discharge of a lamp in a few minutes, but this I want to do first. So example number 2. Okay, example number 2 is the following. First of all, I'm going to put the capacitor here, just because my drawing is, okay, so I'm going to put the capacitor here, okay? And I'm going to put a resistance here, and another resistance over here. So I'm going to have one resistance here, one resistance here. So R1, R2, this is the capacitor, this is the current flowing, I. Again, I'll give VA minus VF to be V0. At t equals 0, I close the switch, and then we're off. And then we've got to decide what happens. So this is also charging a capacitor, but we're using a slightly more complicated circuit. Could anybody actually tell me what the answer is going to be before I start? Could anybody tell me roughly what the answer is going to be before I even start?
What's the question?
Well, I want to write down a differential equation for Q of t, the charge here on this capacitor. So, sorry, I want to write down an equation for Q of t, and it will contain C in it, and V0, and R1 and R2. How do you think it will relate to the first problem we did?
Will be half of the first problem?
Half.
According to K1.
Yeah, yeah.
Your capacitor's also being hit before there's any resistance in the circuit, though. Assuming you're...
Yes, you're sort of right. If you start up, yes, yes, but you have to think that this is distributed, so that's not a real problem. But yeah, what are the yes?
Well, everything's going to be the same. The resistance is just going to be different, but you can add the resistances together in a parallel circuit.
And what will the addition of the resistances give?
1 over R1,
Is 1 over R. I wonder if this gentleman is correct. Let's check. Let's go through our whole set of rules and just see if that is the answer that comes out. Okay, it splits now. I1 goes this way, I2 goes this way. Whoops, that's not it that way. I2 goes this way. All right, now we have a splitting of currents. When you come back down here, you have I2 coming in here. It meets I1 coming down here, so you'll just have I going out there. What's the relation between I1 and I2? Right, so K1 tells me that I is I1 plus I2. K2, I'm going to do ABDF. Now I have to give 2 extra letters here. A, B, D, and I'll put G and H over here. Okay, ABDF. VA minus VB plus VB minus VD plus VD minus VF plus VF minus VA equals 0. What's VA minus VB? Q over C. What's VB minus VD? R1 times I1, right? It's R1 times I1. What's VD minus VF? 0. And what's VF minus VA? Negative V0. Okay, that's that circuit. Let's try another one. BGHD. BGHD. So VB minus VG plus VG minus VH plus VH minus VD plus VD minus VB equals 0. The voltage drops around any closed circuit are 0. So what's VB minus VG? What's that? 0, because I don't have any element there. What's VG minus VH? R2I2, very good. What's VH minus VD? 0. What's VD minus VB? That's correct, negative R1I1 equals 0. Now, of course, I have another circuit. I could go around A, B, G, H, D, F. Will I get any new information from that? No, I won't, because it'll just be the sum of those two things. You see, what will happen if I loop around all this way, it's just the sum of those two things. The R1, I1 will cancel. So I get no new information. How many unknowns do I have? Q, I1, I2, I. How many equations do I have at the moment? 3. 3. And what's the relation between I and Q? I is dq dt. So we know that much. So we have 4 equations. And how many unknowns? 4. Q, I, I1, I2. So we should be okay. Right. Let us eliminate I2 from this equation. We'll eliminate I2 from him. So, I2 from this guy is R1 over R2, I1. Now let's go to this equation and find everything in terms of I. We'll relate I1 to I by this equation. This equation gives me I equals I1, 1 plus R1 over R2. Right? Because I2 is R1, I1 over R2 from this relation. So now I've used him, and now I'm going to use this guy and this guy. All right, from the middle guy, I have Q over C plus R1, I1. So that's R1, but I1 is I over 1 plus R1 over R2. And that's fine, and that's equal to V0. Now, I is dq by dt from this guy. So this equation now is the I is dq by dt. So it's R1, R2. I'm multiplying above and below by R2 over R1 plus R2 dq by dt plus 1 over C times Q equals V0. Are you ever looking good? Because the effective resistance of this circuit the effective resistance is R1, R2 over R1 plus R2. Turn everything upside down. 1 over R is 1 over R1 plus 1 over R2. So this extra loop in the circuit didn't change things very much. It really just, you recognize that you should get the effective resistance. These resistances are in parallel, so the effective resistance due to the effects of both of these is simply 1 over the effective resistance, which I've called capital R, is 1 over R1 plus 1 over R2, the given resistances in the line. Right, so the reason I do this example is it gives you the simplest example of looking at the simplest network, a network with 2 loops in it, or effectively 3 loops, but the third loop doesn't give you independent information. We have 2 loops, and we have to use both Kirchhoff 1 and Kirchhoff 2. But just writing down these very simple relations that at any junction, any node, the current splits, the amount of current in is the sum of the currents out, and then Kirchhoff 2 is around any closed circuit, the total set of voltage drops has to be 0. And just writing these things down, and in a methodical way, just eliminating things, we indeed got an answer that actually makes sense from our high school knowledge that resistances in parallel combine by 1 over R1 plus 1 over R2 is 1 over the effective R. Supposing the resistances were in series, how would they combine? Right. So if I just put 2 resistances here, effectively the effective R would have been R1 plus R2. It's very easy, isn't it? I mean, you could make up your own circuits to do great things, to achieve wonderful yokes. Okay, next example. Next example. Where is that? Oh, there it is. So, example 3. So I'm going to flash a light bulb. So what I'm going to do is I have a circuit like this. I have a resistance. This is where the light bulb is. This is a light bulb. And I have a charge here on the capacitor. I have my little battery in my phone. And so there's Q of t on this. And the resistance R is here. Here's I is dq by dt. And I start off at t equals 0. I start off with a charge Q of 0 is capital Q0. Right. I close the switch. Now I have a closed loop. So I only have Kirchhoff 2 will tell me that R times I here plus 1 over C times Q equals 0, because there's no applied EMF this time. we had charges, effectively our capacitors acting like our driving source. Okay, so this equation is dq by dt plus 1 over RCQ equals 0. And Q at 0, the initial charge, is given as Q0. Well, now the solution to this is very easy. It's so easy, you've done it so many times in radioactive decay. It's just Q0 e to the minus t over RC. The initial current, I of t, is the derivative of this, which is what? It's Q0 over RC times e to the minus t over RC. So, what will I do? I want to get a good flash. So, I'll switch the switch. There'll be a little surge of current. The current will go through here, my light bulb. The light bulb has a nice filament. That's our resistance. That shines. And then I turn the switch off. Because if I leave the switch on, I'm going to drain my battery altogether. Yes, question?
Should I of t be negative?
It should. Thank you. The current goes the other way. Thank you very much. Well done. Question? Same. Well done. Well done. So that means the current flows the other way. So this is, so now, so you just switch it on, switch it off. You know, that's, I think when you click these things, there's an automatic on-off like that. And you get a little surge, and you get a flash, take your picture, everything's happy. Okay, final example. Final example is the LRC circuit. Now, we don't have the equipment to solve this one yet, but we soon will. Towards the middle of the second part of the course, we'll have learned how to solve the equations in this case. Example 4. Is the LRC circuit. Again, I have a switch, a source of EMF, I have an inductance, a capacitance, and a resistance. So A, B, D, F. And we're given that VA minus VF is some function of time. I'm going to allow it be an alternating current. Question?
Yeah, I'm just curious why you're using an alternating current source in these examples rather than DC, like a...
Well, I used a DC all in these cases. V0 was constant, right?
Oh, well, why would you use this for an alternating source?
Well, I could, but I didn't want to. Because I was thinking of, I have a battery that's going to charge something. I don't want it. I don't want alternating current. But if I did, yes, I can handle that. If I did, the equation we would have got, dq by dt plus 1 over RCQ, would have been 1 over R times a sinusoidal function, say, of, you know, the V0 of t would be like sine omega t times V0. Yeah. In the notes, you'll see, actually, I've given you how to solve that particular case. Right. So, again, so the current here, this is L, C, R. So, Kirchhoff 2 says VA minus VB plus VB minus VD plus VD minus VF plus VF minus VA is 0. VA minus VB is L di by dt. Right? From our inductance. The voltage drop across the reductance. Inductance. VB minus VD, that's Q over C. Vd minus Vf, Ri. And Vf minus Va is minus V naught, so I'll bring the V naught to the right-hand side. Again, I is dq by dt, so this becomes a second order equation for Q. A second order ordinary differential equation. And this is our famous LRC circuit. Let me tell you how this gets used. Okay, we have a circuit like this. What we'll find is as follows. If R is in some sense quite small, the solutions, not counting this at all, the solutions of the homogeneous equation, namely this equals 0, will be just oscillations, roughly with frequency 1 over the square root of LC, times a very slow decay. So there'll be oscillations which gradually decay. Now, if you apply a source of alternating current, and the frequency of that source is close to the natural frequency 1 over the square root of LC of this equals 0, then it's like, how do you knock down a bus stop? Yeah, I know this is like, where did he come up with this? I'll report him to Homeland Security. How do you knock down a bus stop? And now the big guys will just crash into it, like, yeah. No, supposing now you want to do it subtly. Yes. You would give it a little hit, and you'd notice that it kind of oscillates like this. And then what would you do? You'd start just hitting it in phase, right? And it's like a kid on a swing. You know, you keep doing it in phase, and the swing swings higher and higher, and the kid is soon screaming his head off. Right? This is called resonance. So the response of an LRC circuit, you can tune the response by choosing your parameters. In this case, you choose the C, the condenser, the C, the capacitor. When you turn the knob on your radio, you change your 1 over square root of LC. And what you'll do to pick up the radio station with a certain frequency, the carrier frequency that you like, classic FM or something like that, I know you guys listen to that, you would tune to that particular frequency. Now, even though your aerial is like this part here, your aerial is getting stuff from all the radio stations, and some of the radio stations are blasting a lot, with a lot more intensity than the one you want to listen to, classic FM. But nevertheless, the one you hear, the one that your circuit responds to, is the one where you have tuned the frequency to be close to the frequency of the carrier of the station you want to listen to. So the signal comes off that, and then of course on the signal, once you take off the wiggly part of the signal, the change in the amplitude is in fact the music you hear. Right? So we'll be learning about this. This is LRC circuit. In fact, this whole thing is a paradigm for lots of things. We'll see effectively why ozone is very good. For our health. The fact that we have ozone in the upper atmosphere essentially it'll be described by an equation very similar to this. Nothing to do with electricity, by the way, but it'll be an equation which is similar. Okay, now what I want you to take away is the following. That to write down all the equations for electric circuits, simple electric circuits, in other words, ones where you have linear relations between voltage drops and currents and charges and things like that, it's very simple. You just have to know the elements and the voltage drop across the various elements and the two rules, Kirchhoff 1 and Kirchhoff 2. After that, it's just plain sailing. But we'll do lots of examples. So, see you.